Okay, so I believe this is today's lecture is going to be the last lecture in this semester, and I will be returning to the last section of this course, so which is the singular value decomposition. So, singular value decomposition. So in order to understand the singular value decomposition, then you will need to understand the structural theorems and positive definite matrices and all those theories that we have studied so far. But the idea of the singular value decomposition is very simple and also very useful. This is well. So this is everything is well. It's just a matter of the four fundamental subspaces of the matrix. So do you remember the four fundamental spaces? Well, considering the matrix A linear transformations between two vector spaces, the domain so has the direct sum decompositions of the column space and the null space. Sorry, the row space and the column null space, and the codomain has the direct sum decomposition of the left null space and the row space, column space. Sorry, confusing. And well, so if you restrict your domain of the linear transformation A to the row space of your vectors, row space of the domain, then A is actually mapping the row space bijectively onto the column space. So there is a, well, so there is an isomorphism between, so A is an isomorphism between the row space and the column space. And the singular value decomposition is going to give you very nice set of bases for your domain and codomain, such that some of them they are going to be a basis of the row space, and some of them are going to be the basis of the column space. And on the other side, some of them are going to be the basis for the column space, and the other ones they're going to be the basis of the left null space. And on top of that, these basis vectors they are all orthogonal bases, so, which is very nice. Okay, so I will try to explain this theorem. So this is the biggest theorem in today's lecture. SVD. So obviously the SVD is short for the singular decomposition. Well, let A be a real and n by n matrix. So well, matrix A may not be a square matrix. So your matrix A could be just matrix of any dimension. And you can find three matrices, U, V, and sigma, satisfying these properties. U is an m by m orthogonal matrix. So you know what I mean by orthogonal matrix. So orthogonal matrix is whose columns of the orthogonal matrix is the orthonormal to each other, right? And well, A is an m by n matrix, and U is, you take this number, and U is an n by n orthogonal matrix, and V is another orthogonal matrix, but which is n by n. So you take this number, and V is an n by n orthogonal matrix. Excuse me. And finally, the sigma. This is the most interesting one. So this is an m by n matrix. So dimension of sigma is the same as the dimension of matrix A. So this is this is m by n, and this is m by n. And I say this matrix sigma is an almost diagonal matrix. Hey, how can I say a possibly non-square matrix is diagonal? So well, this equation gives us the idea what I mean by the almost diagonal matrix. So the ij component of this matrix sigma is 0 if I is different from j. So therefore, so possibly non-zero entry of this matrix sigma is going to be these entries, right? So these entries may or may not be 0. but all the other entries, they are automatically 0. So in this sense, I say the sigma is an almost diagonal matrix. Okay, all right. And the conclusion of the theorem is I can find these three matrices, U, V, and sigma, such that A is U times sigma times and V transpose. So I will try to explain how can I find such matrix U, sigma, and V, and what are the meanings lying underneath. Okay, to prove the theorem, so I'll try to break down the proof into few different parts. So claim number one is a non-negative real number lambda is an eigenvalue of A transpose if and only if lambda is an eigenvalue of A transpose and A. Before I prove the claim number one, so first you will need to understand. So AAT and ATA, they are both real and symmetric matrix, right? And according to the spectral theorem, every real symmetric matrix has the real eigenvalues, and they can be orthogonally diagonally, right? Oh, hold on. So just one more thing. These two matrices, they are both positive semi-definite matrix. Do you remember the meaning of definition of the positive semi-definite? Previously, so I have introduced the five or four. So I don't remember. There are four equivalent criteria that tells us if any given matrix is a positive definite or not. So there was the last criteria was this: a square matrix is positive definite if and only if you can find another matrix R such that R transpose times R equals to A. Right? Okay. So if you can find such, well, and also the matrix R must be a full rank matrix. If you can find such a nice matrix R, then that is equivalent to say the matrix A is the positive definite. Okay. But hey, what if the matrix R is a non, well, what if your matrix A is not a full rank matrix? If the rank matrix A is not a full rank matrix, then that is, well, then this time around, then your matrix A sometimes be the quadratic form of the A, so A transpose times A times X might be 0 for some non-zero vector X, right? Because, well, if your matrix A has some non-trivial null space, then that implies you can plug in some non-zero numbers, non-zero vectors, xt and x over here and there, and whose answer equals to 0, right? So I mean, well, and since there is no assumption that A is a full rank matrix, therefore AAT and ATA, they can be assumed as a positive, not positive definite, but positive semi-definite. And if the matrix is positive semi-definite, then the eigenvalue should be not strictly greater than 0, but eigenvalues must be always non-negative, right? Okay, great. So, AAT and ATA, they have non-negative real eigenvalues, lambda. And this says, so lambda is an eigenvalue of AAT if and only if the same number is the eigenvalue of ATA. Okay, all right, so so much for the explanation. So now let me go to the proof of the statement. Well, suppose that lambda is an eigenvalue of AAT. Then by definition of the eigenvalue, AAT times X is lambda times X, but multiplying the both sides, A transpose to the left of the equation, then we have this, but well, this guy is just lambda times A transpose times X. But if you look at this equation very carefully, not very carefully, but if you look at this equation, then ATA times ATX is lambda times ATX, right? So, so that means lambda is an eigenvalue of ATA, and whose eigenvector is AT times X. Okay. So if lambda is an eigenvalue of AAT, then lambda is an eigenvalue of ATA. And the converse is the converse statement can be proved in very similar way. So I will just skip it. And claim number 2. This is also very obvious. Is it obvious? Well, this is not that obvious, but we have already discussed this theorem, this statement, long time ago, before. So I won't spend much time explaining it just one more time. So let me just take this for granted. So these three matrices, A and ATA and AAT, they all have the same rank. And I'm going to simply say the rank is the R. Okay. And by spectral theorem, so since these two matrices are the symmetric matrices, actually they are positive semi-definite symmetric matrices. So they allow a orthogonal diagonalizations. So I say so U lambda 1 UT and V lambda 2 and VT. So we have these two orthogonal diagonalizations, but I will just focus on the second diagonalization. This one. So, well, this is an orthogonal diagonalization of ATA. So this is the unit eigenvectors of this vector. This matrix V has columns of the orthonormal eigenvectors of ATA, right? Hold a second. So I want to talk about, so I really want to mention about the dimension of this matrix. Since we were assuming that A is an n by n matrix, n by n, therefore ATA, which is n by n, right? So V is an n by n matrix, and this is an n by n matrix, and this is another n by n. This is still n by n matrix. And clearly, this middle matrix is diagonal matrix that whose diagonal entries are just simply the eigenvalues of ATA. Okay, so well, but our convention is we always put the top left corner, the largest eigenvalue. So the largest eigenvalue is always going to be lambda 1. And the second to the largest is going to be lambda 2 and da da da. And the least positive eigenvalue is going to be lambda R. And all the and also this guy is positive semi-definite, so there is still possibility of having the zero eigenvalues, and all the other eigenvalues, so all these zero eigenvalues goes to this bottom right corner. Just one more thing. How many non-zero eigenvalues can you find? In this case, since we were assuming the rank of this matrix is R, right? Therefore, there should be precisely R many non-zero eigenvalues of ATA, right? Because the number of the zero eigenvalues is going to be the number of the null space of the dimension of the null space. So since this rank of the matrix is R, therefore you should have precisely R many non-zero eigenvalues for ATA. So lambda 1 is the largest one. So greatest one to the least one, and they are because of our construction or because of our convention, these numbers they are all strictly positive numbers, right? Because this is the greatest and this is the least one, the least positive eigenvalue. So they are all strictly positive, and every strictly positive numbers can be written as the square root of something. So I say, so I am introducing the numbers sigma 1 to sigma r, and sigma 1 is merely the square root of lambda 1, and sigma 2 is the square root of lambda 2, and sigma r is the square root of lambda r. And also these numbers, sigmas, so so it also respecting these inequalities. So sigma 1 is the largest and sigma r is the least. And these numbers, sigma, they are called the singular values of the matrix A. So these numbers are the singular values. Okay. All right. So these numbers, they are all greater than 0. These are eigenvalues, and we have exactly how many non-zero eigenvalues of ATA. Okay. Good. Now, so let me turn to these orthonormal eigenvectors, V. So this is my vector V. So this is an n by n matrix, and I'm going to call the columns of the matrix V to be from V1 to Vn. And because of our construction, these vectors V1 to Vn, they are the eigenvectors of ATA. So multiplying these vectors to the right of the matrix ATA, so ATA times Vj, then since these are eigenvectors, so it's the lambda j times Vj, but well, by our definition of the singular values, so lambda j is sigma j squared, and this relation is true for j is 1 to r, right? So if j is greater than if this index j is greater than r, then this is simply 0. AT times A, so say for instance, like ATA times VR plus 1 is going to be 0, right? Because this eigenvalue is 0. So this relation is only true for the indices between 1 to r. Right? Okay, so anyway, we have this relation over here, and if you multiply the both sides of the equation by matrix A to the left, then ATAVJ is sigma j times AVJ. And looking at this equation very carefully, then this vector the vector A times Vj is an eigenvector of AAT with eigenvalue lambda j, which is the sigma j squared. Okay. So we also found the eigenvectors of AAT. Some eigenvectors, not all eigenvectors, but also I want to compute the length of these eigenvectors AVJ. So to find the length of this vector, I just take the length square of this guy. But the length square is with nothing but taking inner product with itself. So VJT AT times AVJ. But you know what? So Vj was defined to be the eigenvector of ATA. So ATA Vj can be replaced by sigma j times Vj. So sigma j square times Vj. Therefore, sigma j square and length of Vj squared. Okay. But so we said this is an orthogonal vector. So every column has length 1. So this guy is 1. So this is simply Vj squared. So taking square root to the both sides of this equation, so we conclude that the length of this eigenvector Vj, AVJ, is sigma j. Okay, so I also want to emphasize on the dimensions of each of these vectors. So this vector Vj, this is an n-dimensional vector, right? But A times Vj, this is an r-dimensional vector. Sorry, n-dimensional vector, right? Sorry, this is an m-dimensional vector. This is an eigenvector whose length is this singular value. So dividing this vector by its own ranks. I mean, so if you normalize this vector, and this is the normalization of this eigenvector, and this is a unit eigenvector of AAT, and whose eigenvalue is sigma j squared. Okay. All right. Now, so I want to say, so I want to define this guy to be uj. This unit eigenvector, so is now uj, and multiplying both sides by the singular values, then avj is the sigma j times uj. So again, this equation is also true for the indices between 1 to r. Okay. All right. So so what we have been so what I was doing so far is I found the eigenvectors of ATA, and we had the orthonormal eigenvectors from V1 to VR satisfying this relation. Satisfying this relation. So V1 to VR, they are the orthonormal eigenvectors, and this is an also eigenvector of AAT. The question is, are they linearly independent? Well, by our constructions, V1 to VR, they are automatically linearly dependent because they are orthonormal vectors. But are they linearly independent to these vectors? So we obtain the vectors from U1 to UR. So U1 to UR. So we have R many such vectors. And I want to make sure that these vectors are linearly independent. And actually, they are linearly independent. Why? Because if two indices are different, so I tried to take the inner product of UI and UJ. And UI, by our definition, UI is the 1 over U sigma I times AVI, and UJ is 1 over sigma J times AVJ. And expanding this, we have this, but VJ was assumed to be the eigenvector of the ATA. So this guy can be replaced by sigma J squared times VJ. But you know what? So here, VI transpose VJ. So this is, well, 0, right? Because we are assuming the indices are different. And these eigenvectors, Vi and Vj, they were chosen from these column vectors, and they were orthonormal vectors, right? So taking inner product of two different eigenvectors, that we must have 0, right? So that means if Vi and Vj are orthogonal to each other, then Ui and Uj, they are again orthogonal to each other. And every orthogonal vectors, they are automatically linearly independent, right? So that means U1 to UR is an orthonormal eigenvectors of AAT. Okay. All right. So what is the point of this entire discussion? So you might be wondering. And these are actually very nice and important basis vectors for the domain and codomain. So which I will explain from now on. Okay, so at the very beginning, so we have assumed the rank of the matrix A is R, and therefore the dimension of the column space and dimension of the row space, they all have the dimension, they are all R, right? And A maps the row space bijectively onto the column space of it. Okay, so this is very easy. Now we want to take a look at these vectors. Now we have obtained R linearly independent vectors that lives in the m-dimensional Euclidean space, right? So, and I claim that these vectors are in the column space of A. Why? So what is the definition? Well, what is the column space? The column space is actually the image of the linear transformation A, right? So so linear A can be considered as a linear transformation from Rn to Rm. Well, and you take the image of Rn, domain Rn, in the codomain Rm, then this image can be considered as, well, should be understood as the column space. And these vectors U1 to U1 to UR, they are actually the image of 1 over sigma j times Vj under the linear transformation A, right? So these guys are the image of the linear transformation A. Therefore, they are in the column space of A, right? And we know that this guy, the column space, is R-dimensional vector space, and we happens to have R many linearly independent vectors that lives in C of A, column space of A. So these vectors, they can be an orthonormal basis of the column space. Okay. Okay. Good. And yeah, I consider this relation is very important. This relation is very important. So AVJ is the sigma j times UJ. And this relation tells us, this relation is true for J from index from 1 to R. So, and these vectors, so these vectors V1 to VR, now they are the vectors that lives in not codomain, but they living in the domain of the linear transformation A, right? And A is actually isomorphism between the row space to the column space. And these vectors, well, so this relation tells us this equation tells us the relation between the basis vectors V1 to VR and basis vectors U1 to UR. So every basis vector V1 to VR is, their images are sigma times singular value times basis vector Uj. That means, well, there is clearly a isomorphism between the space spanned by these basis vectors and that basis vector, right? And this is also an R-dimensional vector space in the domain of the linear transformation A. So this is an R-dimensional vector space in the domain. And under the matrix of linear transformation A, this R-dimensional vector space is now mapping bijectively onto the R-dimensional space spanned by these vectors. But this space is, we know, the column space. And there's only one space that maps to the column that maps bijectively onto the column space under the linear transformation A. What is that? That is the row space, right? So that means these vectors, they are the basis vectors of the row space. Okay. So isn't it great? So, well, just some computation. So, well, we apply the spectral theorem to this positive semi-definite matrix. And we have chosen the first R columns from the matrix B. And so V1 to VR. And these vectors from V1 to VR, they are the not only basis, but the orthonormal basis of a row space. And their images, these vectors, V1 to VR, their images under the linear transformation A is a orthogonal basis for the column space. And normalizing them, so we have the orthonormal basis. So with this simple computation, we have obtained the orthonormal basis for the row space and the orthonormal basis for the column space. And we also know how these basis vectors for these two spaces are related to each other, just by this very simple and elegant equation. Okay, so all right. Okay. So now we have the basis vectors for the column space and the row space. We have the orthonormal basis vectors for the column space and row space. Okay, what about the orthogonal complement? Well, what is the orthogonal complement of the row space? Orthogonal complement of the row space is the null space of A, and the orthogonal complement of the column space is the left null space. So we also need to find the basis of these orthogonal complements. Finding the basis for the null space is easy. Why? Because, well, every orthonormal basis every orthogonal vectors that which is so let me try just one more time. So every set of vectors that is orthogonal to this space spanned by these guys, they are going to be the basis for the null space, right? But, well, so these basis vectors from V1 to VR was chosen from the first R columns from the matrix V. But then taking the rest n minus R vectors from here, not from there, but from here, from VR plus 1 to Vn, because of these guys are orthogonal matrix, the vectors from VR plus 1 to Vn, they are going to be the basis vectors for the null space, right? Because these vectors, this is clearly orthogonal to this space, right? And these basis vectors are clearly the n minus R dimensional the space spanned by these vectors. It's going to be the dimension of the space going to be n minus R, which is precisely the same as the dimension of the null space. So these vectors are going to be the basis of the orthogonal complement of CA transpose row space, which is the null space, right? So we also obtained the orthonormal basis for the null space. What about the orthogonal basis for the left null space? Likewise, we can find the basis vectors. So we can find n minus R for basis vectors that spans the orthogonal complement of the column space. So that is going to be the basis of the left null space. So how do we find such a basis vector? My first idea is maybe you can try applying the Gram-Schmidt process to this orthogonal basis, so orthogonal complement. You can do that, but the another idea is if you apply the spectral theorem on AAT. So applying the spectral, so this is still positive semi-definite symmetric matrix, so you can apply the spectral theorem. And well, AAT has the same eigenvalues as A transpose as A. So lambda 1 here, lambda 2 there, lambda R here. And we know that these vectors from U1 to UR, they are the orthonormal eigenvectors of AA transpose, right? Okay, so, okay, what does that? Yeah, so AV, so this is some scalar multiple of UI, whose eigenvalue is lambda J. So therefore, these vectors are going to be the eigenvectors of these eigenvalues. But because of the spectral theorem, these basis vectors, they are still orthogonal vectors, but these guys, they are orthogonal to the space spanned by these vectors. So therefore, these guys are orthogonal to the column space of A. So that means these basis vectors are going to be the basis for the orthogonal complement of the column space. Okay, so by doing so, now we finally have the full set of basis vectors for the domain and codomain. For the domain, of the linear transformation A, we have these guys are the basis vectors for the domain, right? V1 to Vr spans the row space, and Vr plus 1 to Vn spans the null space. Okay. And for the codomain, U1 to Ur spans the column space, and Ur plus 1 to Um, they span the left null space. Okay. And especially between V1 to Vr and U1 to Ur, they are enjoying this very nice relation. Okay. Okay. All right. So okay. So I summarize that what I have spelled out so far. So we obtained the basis vectors from V1 to Vr and U1 to Ur, and these vectors, they are enjoying this very nice property, and this is the singular value of your matrix A. And if your index J is greater than R, then A times Vj should be 0. Why? Because if index J is greater than R, then these vectors are the basis of the null space, right? Therefore, A times Vj should be 0 if your index J is greater than R, right? But well, well, for future purpose, I have just written down that this guy is the 0 times Ur plus 1, right? So, okay, I can summarize these relations in just one single matrix equation like this. A, which is n by n matrix, A multiplied by this column vector V1 is sigma 1 times U1, right? A times V2 is sigma 2 times U2, right? A times VR is sigma R times UR. Okay, but A times VR plus 1 is just a bunch of zeros, right? So I have this matrix equation, and this is an orthogonal matrix, and this is an orthogonal matrix. This is an n by n orthogonal matrix, and this is n by n orthogonal matrix. So I gave them the names. So from now on, I'm going to call this guy the matrix B. This guy is U, and this guy is sigma. Okay. And multiplying the both sides by V transpose, I have A is U times sigma times V transpose. Okay. Okay, good. So this proves the theorem of the singularity composition. So I believe this is the right time to give you a brief summary of what we have been doing so far. So this is the domain. So if A is an n by n matrix, then domain is the n-dimensional vector space, and codomain is the m-dimensional vector space. And domain has this direct sum decomposition of the row space and the null space. And codomain has the direct sum decomposition of the column space and the left null space. And if we are assuming the rank of the matrix A is R, then this is R dimension, and this guy has a complementary dimensions, which is n minus R. This R dimensional space, and this is m minus R dimensional space. And well, every vector in this space goes to 0, right? But A maps this row space bijectively onto the column space. So this guy is being mapped bijectively to be here. So, and well, with the spectral theorem, so we have obtained the orthonormal basis vectors V1 to Vn and U1 to Um. And V1 to Vr, they are enjoying this nice property. And if J is greater than R, then AVJ equals to 0. This implies these basis vectors, U1 to UR is the orthonormal basis of the column space. And UR plus 1 to UM is the orthonormal basis of the left null space. And V1 to VR is orthonormal basis of the row space. And VR plus 1 to Vn is the orthonormal basis of the left null, null space. So, well, the whole point of the singular value decomposition is about the finding the nice basis of the domain and codomain. So, if under the algorithm of the singular value decomposition will give you the basis vectors of the domain and codomain, and they are enjoying very nice properties. First, they are orthonormal basis, right? And first, R vectors are going to be the basis for the column or row spaces, and the other basis vectors are the basis for the they are orthogonal complement. And on top of that, they are enjoying this very simple relation. So it explicitly gives us a relation how these basis vectors are related to each other. Okay, isn't that great? Nice. Okay, never mind. Okay, so much for the theory. So I will now turn to some very concrete computation. I will find the singular value decomposition of this matrix, this column vector. Oh, hold on. So can I find a singular value decomposition for a column vector? Oh, yes, you can, because a column vector can be considered as a 3x1 matrix, right? So you can technically you can apply the singular value decomposition. All right. So in order to implement the singular value decomposition, first I will try applying the spectral theorem to A transpose of A. So if this is A, then this is A transpose and A, and multiplying this, you have a just 1x1 matrix, which is just 9. And what do you think is the orthogonal diagonalization of this matrix? It's just 1 times 9 times 1. Okay. So this vector 1 is just a eigenvector of eigenvalue 9. So this guy has eigenvalue 9 with eigenvector 1. Very silly, right? Okay. So I obtained the vector v1, and from vector v1, now I will try to find the basis vector u1. Right? How do I get this basis vector u1? If I multiply A times v1, I'm gonna get some number times and I'm gonna express this vector by some positive number times a unit vector. Then this positive number is gonna be the singular value, right? So if you multiply this vector v1 here, then which is simply matrix A itself, right? But what is the length of this vector? Length of this vector is 9, 3, right? So dividing everything by 3, normalizing this is going to be my u1, right? And this vector can be considered as 3 times u1, right? Here, 3 is, well, so 3 is the singular value of the matrix A, as expected. Well, because this is not very surprising, because my eigenvalue was 9. Therefore, our singular value should be the square root of 9, which is 3. So because of this reason, it is not surprising that the length of this vector is 3, right? So our first singular value is 3. And our first and last singular value was 3. And okay, so we are good. We now have the basis vector v1. This guy spans the row space of the domain of A, and this guy spans the column space of the this guy spans the column space of A. But we are not quite done yet. So in order to get the full singular value decomposition, we still need to find the orthonormal basis that spans the orthogonal complement spanned by this vector. Okay. So in order to find that such orthonormal basis vectors, then we actually need to orthogonally diagonalize this positive definite matrix, positive semi-definite matrix. So AAT, which is this, and after some tedious computation, it turns out the first eigenvalue is 9, and the second eigenvalue is 0. I have but again, so as expected, so its eigenvalue is the same as U1, right? But for eigenvalue 0, we have two orthonormal eigenvectors that spans the eigenspace of 0, right? But this is also very clear because the rank of this matrix is 1. So we have one non-zero eigenvalue and two eigenvectors of eigenvalue 0. Okay, so therefore A is this vector goes to here, and this vector goes to here, and that vector goes to here. So this is my matrix U, right? And what is my matrix? My matrix, almost diagonal matrix sigma, is going to be this, right? So dimension of sigma, I told you the dimension of the sigma was the same as dimension of matrix A, and whose diagonal entries are the singular values of your matrix. But however, my eigenvalue was 9, so my singular value should be 3, right? So 3, 0, 0, and followed by this matrix 1 transpose. So this is the singular value decomposition of this matrix. Okay. If you feel like the previous exercise was too easy, so now let me turn to something more complicated, like this one. I will try to find the singular value decomposition of this 2x3 matrix. Before I begin the exercise, what is the rank of this matrix? Which is 2, right? So therefore, I must be able to find two different singular values for this matrix, right? So just like before, so I will begin from diagonalizing this this metric matrix ATA. So this is A, and this is my ATA. And again, because of our tedious computation, so we have two non-zero eigenvectors, 3 and 1. But which is not that surprising. Why? Because the rank of this guy was 2. Therefore, so I must have two non-zero eigenvalues for ATA, right? So the first one was 3, and the second one was 1, and the orthonormal eigenvector, unit eigenvector of this guy was this, and I will call this guy to be V1, and orthogonal unit eigenvector of this guy, which was this, and I'm going to call this guy V2 for 0 eigenvalue, and I also normalize the eigenvector, and I'm going to say this is my V2. Okay. All right. So we have V1, V2, and V3. But I am not that interested in this eigenvector because this eigenvector is for the eigenvalue 0. So in order to get eigenvalues U1 and U2, so we actually have to multiply matrix A by this eigenvector V1. A times V1, so which is this. So since this is 2x3 matrix, 2x2 matrix multiply the 3x1 column vector, then the result can be written as the unit vector times the length of this vector. So which is square root of 3. But this number again was expected because this number should be precisely the square root of this first eigenvalue, right? And because of our construction, so this unit vector should be called as U1, right? And likewise, this V vector V2 multiplied by the matrix A, then which is this, and normalizing this, writing down this guy as a unit vector times its own length. So whose length was just 1 and times this one. And again, so this unit vector should be called U2. And the length of this vector was 1. But again, this was also expected because 1 is the square root of this number. Okay. And well, for this exercise, I do not need to diagonalize the matrix AAT. Why? Why is that? Because the rank of this guy was 2. So therefore, the column space, the dimension of the column space is also 2. So column space of this matrix A actually spans the entire codomain of this linear transformation. Right? Therefore, that means for this matrix, there is no such left null space. Well, there is a left null space, but it is a trivial space. Right? So therefore, you do not need to find the basis vectors for this left null space. That is why I do not need to apply the also diagonalization of AA transpose. So, I mean, in other words, I do not need to pick these vectors for the basis for the left null space. This procedure is not necessary. So I have U1 and U2. So the first vector goes to here and second vector goes to there. So I have 2 by 2 orthogonal vectors, orthogonal matrix U, and my almost diagonal matrix sigma, so whose first diagonal entry is the square root of 3, which is the square root of first eigenvector. And the second singular value is the square root of the second eigenvalue. And all the other entries equals to 0. And for this matrix B, the first entry is this guy, and the second entry is that guy, and the final entry is that guy. And of course, you need to transpose this. If you take a transpose of this final matrix and multiply them together, then you can easily convince yourself that the entire matrix is just your original matrix A. Okay. So this is the singular value decomposition. I have no idea why I'm giving you another summary of the singular value decomposition, but why not? So, for any real n by n matrix with rank R, so first we diagonalize A transpose of A, then we obtain these n orthonormal unit vectors. And for these first R vectors, we have A times Vi is the Ui times sigma I, and this is unit vector. And so these vectors, they are going to be the first R vectors for your matrix U, right? So this is m by m, this is n by n, this is n by n. So this first R vectors obtained by this relation is going to, goes to here. And for this rest n minus R vectors, these vectors are obtained by, applying the diagonalization of the AAT, right? And these vectors, we want to Vn, goes to here as a row vector, not column vector, as a row vector, because this guy has been transposed. So, and this first R vectors is the orthonormal basis of the row space, and this rest n minus R vectors, they are orthonormal basis of the null space. So, and this factorization, so this decomposition is working like this. Suppose that you are multiplying basis vector V1 over here. Then that is the same as multiplying the basis vector V1, the column vector V1 over here, right? But if you have the column vector V1 over here, then V1 inner product with this guy is going to be 1. But V1 inner product with the second vector is going to be 0, right? Because they are orthonormal basis, right? So if you multiply V1 over here, then the resulting column vector is going to be 1, 0, 0, 0, 0. Okay. And if you multiply this 1, 0, 0, 0 to the right of this matrix, then what you're going to get is n by 1 matrix, which is the sigma 1 and 0, 0, 0, 0. Right? And finally, if you multiply sigma 1, 0, 0, 0 to here, then finally you will have sigma 1, u1, sigma 1 and u1. That's it. So because of this reason, so this decomposition is precisely gives us so how these eigenvectors are related to each other. Okay. So this is the singular value decomposition. Okay, so all right, so now I know it's a singular value decomposition, which is very nice. But what is the purpose of this entire computation? So why do you even need to spend time and effort to study the singular value decomposition? Well, there are many reasons, but the most important application of the singular value decomposition is a pseudo inverse. So what is a pseudo inverse? Well, technically, so in principle, the inverse matrix is only defined for the square matrix, right? If your matrix is not square, then you cannot define any inverse. But pseudo inverse, which is not exactly inverse, but pseudo inverse can be defined for possibly non-square matrices. How? Well, even though your matrix A is a non-square matrix, but there is a isomorphism. There is a bijection between the row space and the column space. So such an isomorphism is the crucial. So you cannot break it. So there is always isomorphism between the row space and the column space. Well, even though you cannot define the inverse of the non-square matrix A, but you can somehow make an inverse for between the row space and the column space because they are isomorphic, right? They have bijection. Well, if we restrict ourselves to the row space and the column space, then probably you can define the inverse map, inverse linear transformation between these two spaces, right? So that pseudo inverse is precisely that inverse. The inverse between the row space and the column space. Okay, so I will try to explain from now on. Okay, so this is a little motivation for the pseudo inverse. I will first begin from the overdetermined system. So do you remember the overdetermined system? Well, overdetermined system is a linear system of linear equations whose number of unknowns, whose number of equation is greater than the number of unknowns. So that means most likely you cannot find any solution for that overdetermined system, right? So that is an overdetermined system. So, well, in this context, so A is an n by n matrix and n is greater than n, then AX equals to B is an overdetermined system, okay? So, well, usually you cannot find you cannot find the solution of the overdetermined system unless B is a member of the column space. But even if your B is not a member of the column space, you can still try to find a solution, which is called the least square solution. Do you remember this? So how do you find the least square solution? In order to find the least square solution, we actually need to consider the normal equation, right? This was the normal equation. And if you can solve this equation for x, then that x is called the least square solution. Okay. But how can I solve this normal equation? Well, in order to solve the normal equation, this matrix, this square matrix, ATA should be invertible matrix, right? But this guy, well, so here, so we are assuming that A is an n by n. So ATA should be an n by n matrix, and n by n matrix is invertible if and only if the rank of ATA is n, right? But again, this rank of this guy is same as the rank of A. So, well, this guy, well, in other words, this guy is invertible if and only if A is a full length matrix. Okay. So previously, so to find the least square solution, so A must be a full length matrix. Okay. But what if not? So if A is not a full length matrix, then in that case, this guy is not invertible. So you cannot find such a nice least square solution. And in that chapter, so long time ago, we have not discussed anything about the case when A was not a full length matrix. Well, I tried to draw a little cartoonish picture that describing this entire situation. Suppose that, okay, let us consider this. A is an 3x2 matrix, and which is a full length matrix. So this is a full length matrix. So therefore, the rank of A should be 2, right? Therefore, the dimension of the color row space and the dimension of the column space should be also 2, right? And well, to make things simple, so I say this entire space UV plane is the row space, and this XY plane, not entire plane, but this XY plane in this 3-dimensional space is, let me say this is the column space of this matrix A. Okay. Well, for this overdetermined system, if this B is, the vector B is not a, if vector B is a member of the column space, then since there is a bijection between the row space and the column space, so therefore you can find exactly one vector whose image is this guy, right? But if your vector B is not a member of the column space, then the normal equation was about this. So you try to project this guy to the column space of this matrix A, then you can find the inverse image, unique inverse image of this guy, right? And this guy, whose image is not B itself, but the image of this guy is the column space component of the vector B. This vector, this red vector over here, is there is a unique vector which I will call x hat in the domain A. So this guy is called the least square solution of the normal equation. So this is the geometric description of the normal equation, right? In the case when A is a full length matrix. Okay. What if A is not a full length matrix? If A, so well, now suppose that A is a 3x3 matrix, but whose rank is 2. Well, assume that, so let me say that the UV plane is the row space, and the XY plane is the column space. And if B is, even if, well, in this case, even though you project this, your vector B onto the column space of A, but there is a vector, but in this case, there is a isomorphism between UV plane and XY plane. So that means there is a unique vector in this row space whose image is precisely the column space component of B, right? But, well, you can find infinitely many other solutions than this one. Why? Because let me consider this guy. So this vector has the same component XR, same row space component XR, but it has some non-trivial component in the null space of A. What do you think is the image of this guy? Well, this null space component is going to be mapped to the 0, so can be ignored. Therefore, the image of this guy under this linear transformation is still this column space component of B, right? So if A is not a full-length matrix, there is still a vector in X vector in the row space XR, whose image is this one. This is this vector, so this is a unique vector XR in the row space. But however, XR plus any arbitrary null space vector Xn, it has the same image as XR, right? So this guy and this guy, they have the same image. That means, well, in other words, if A is not a full-length matrix, the solution of the normal equation exists, but it is not unique, right? So every vector whose endpoint is on this line should be the solution of the normal equation. Okay. All right. Okay, but we are not giving up at this point. So this is our new objective. Okay, for normal equation, if A is not a full-length matrix, then now we all agree that this normal equation has a solution, but so it has infinitely many solutions. But what I want is, I want to find the shortest length solution of this normal equation. So these are the vectors whose endpoint is on this line. They are all the solution of the normal equation. But what do you think is the shortest length solution? Which is this guy, XR, right? This guy is the shortest length solution whose image is precisely column space component of B. So I want to find this guy. Okay, so this is the end of the motivation. Oh. All right. So in order to find, okay, now in order to define the pseudo inverse, first I will need to define the sigma plus matrix. Okay, let sigma be an almost diagonal matrix. Okay, you know what I mean by almost diagonal matrix. So sigma is an almost diagonal matrix, which is n by n. Then sigma plus is an n by n matrix, such that defined by this mysterious definition. Well, this definition looks somehow weird, but well, this is not that complicated. So it says, well, because of this, the sigma plus is again almost a diagonal matrix, and sigma plus is obtained like this. If your sigma is n by n, then sigma plus is n by m, right? And well, so this is almost like taking a transpose of this matrix, but not exactly transpose. If your diagonal matrices are some non-zero numbers, then these non-zero diagonal entries taken reciprocal to each other, right? So this is the sigma plus. Okay, and well, and if your diagonal entry is equal to 0, then they just carry over. All right, finally, I can define the pseudo inverse. A, okay, A is an n by n matrix. Then we consider a singular value decomposition, just like this. And the pseudo inverse, which will be denoted by A plus of the original matrix A, is this is, if this is n by n, this is n by m, defined by V times, so well, order has been reversed, V times, now this sigma is now sigma plus and U transpose. This is the pseudo inverse. Okay, so what is the point of the pseudo inverse? Well, so this relation was the key relation for the singular value decomposition. Then if this relation gave us a singular value decomposition of A, then A plus is these V's are over here, and this is sigma plus, right? So these numbers taken the reciprocals, and well, these are the vectors U. Then if you multiply the column vector U1 over here, then it's going to be 1, 0, 0, 0, and multiply over here, then sigma 1 inverse, and sigma 1 inverse is 0, 0, 0, and multiply by here, then you have sigma 1 inverse times V1, right? So for generalizing this, well, A plus times this vector ui was just 1 over singular value times vi, right? And this relation is true for the indices between 1 to r. And if your index is greater than r, then what? Then this is going to be just simply 0, right? Okay. Okay. Finally, so AV times A plus. So, well, if you compose this A by A plus, then AV is sigma I ui, but sigma I ui under A plus, you will have VUI, right? And A times A plus ui is still ui. So just considering the, and you have to remember these vectors, vi and ui, they were the basis vectors for the row space and the column spaces. And for these row space and for these basis vectors, so they remains unchanged under A plus A or AA plus, right? If the basis, all the basis vectors are unchanged, then you are safe to say these linear transformations, well, on the row space and the column spaces, they are precisely the identity matrix. So, well, this is our original scenario. So A is mapping row space to column space, and A plus, well, then A plus is mapping column space to row space, right? And composing these two, they are the identity maps on these subspaces, right? So, well, if this is A, well, then A maps to here. Then under A plus, now this is going to be 0. This is going to be the same point, right? So, and here, under A plus, you start from this point, and you go to here, and again apply by A, then you will arrive at the same point. And, but for this null space goes to 0, and the left null space goes to 0 under A plus. Okay. So, well, so therefore pseudo inverse is, so if A is n by n, then A pseudo inverse A plus is n by n, which is not technically precisely inverse, but if you're just considering the relation between the row space and column space, then this is precisely the inverse. Okay. Okay, sorry. Okay, now why pseudo inverse is something to do with this least square solution, so shortest length solution. So I will explain from now. So if this is B, then this is the column space component of B, and we are looking for this vector that lives in the row space of A, whose image is precisely this guy. This is what we are looking for, right? But what if I apply A plus, the pseudo inverse of this vector? Then, well, first you have to notice that this pseudo, so B can be written as the left null space component and the column space component, right? But under a pseudo inverse, this component is now mapped to the 0, right? And this component will be mapped to this point, right? Because A plus is precisely inverse of A for this row space and column space, right? So this guy is being mapped to here. So A plus times B is precisely the shortest length solution that we are looking for. Agreed? So consider the overdetermined system, then the shortest length solution of the normal equation is A plus B, this guy. Okay. Yeah. So, well, I try to write down everything in equations, but this entire discussion is just captured in this single cartoonish picture over here. Okay. Right. So this is the end of the story, and I really appreciate your patience. Yeah, I know I have lost so significant portion of the audience during the semester, but I really thanks for those of you who choose to remain in this classroom. Thank you very much. And also on this Thursday there will be no lecture, but I'll be just chilling here at this time. So if you have any questions, just why don't you come and visit me in this classroom? Okay, good. See you on next Monday, right? Yeah.